For reading and rereading the manuscript, ensuring that we mean what we say and say what we mean, we are indebted to Robert Lupton of Princeton University. His tandem expertise in astrophysics and the English language allowed the book to reach several notches higher than we had otherwise imagined for it. We are also grateful to Sean Carroll at Chicago's Fermi Institute, Tobias Owen of the University of Hawaii, Stephen Soder of the American Museum of Natural History, Larry Squire of UC San Diego, Michael Strauss of Princeton University, and PBS Nova producer Tom Levinson for key suggestions that improved several parts of the book. For expressing confidence in the project from the beginning, we thank Betsy Lerner of the Gernert Agency, who saw our manuscript not only as a book but also as an expression of deep interest in the cosmos, deserving the broadest possible audience with whom to share the love. Major portions of Part 2 and scattered portions of Parts 1 and 3 first appeared as essays in Natural History magazine by NDT. For this, he is grateful to Peter Brown, the magazine's editor-in-chief, and especially to Avis Lang, their senior editor, who continues to work heroically as a learned literary shepherd to NDT's writing efforts. The authors further recognize support from the Sloan Foundation in the writing and preparation of this book. We continue to admire their legacy of support for projects such as this. Neil deGrasse Tyson, New York City. Donald Goldsmith, Berkeley, California, June 2004. A Meditation on the Origins of Science and the Science of Origins. A new synthesis of scientific knowledge has emerged and continues to flourish. In recent years, the answers to questions about our cosmic origins have not come solely from the domain of astrophysics. Working under the umbrella of emergent fields with names such as astrochemistry, astrobiology, and astroparticle physics, astrophysicists have recognized that they can benefit greatly from the collaborative infusion of other sciences. To invoke multiple branches of science when answering the question, where did we come from? Empowers investigators with a previously unimagined breadth and depth of insight into how the universe works. In Origins, 14 billion years of cosmic evolution, we introduce the reader to this new synthesis of knowledge, which allows us to address not only the origin of the universe but also the origin of the largest structures that matter has formed, the origin of the stars that light the cosmos, the origin of planets that offer the likeliest sites for life, and the origin of life itself on one or more of those planets. Humans remain fascinated with the topic of origins for many reasons, both logical and emotional. We can hardly comprehend the essence of anything without knowing where it came from. And of all the stories that we hear, those that recount our own origins engender the deepest resonance within us. Self-centeredness bred into our bones by our evolution and experience on Earth has led us naturally to focus on local events and phenomena in the retelling of most origin stories. However, every advance in our knowledge of the cosmos has revealed that we live on a cosmic speck of dust, orbiting a mediocre star in the far suburbs of a common sort of galaxy, among 100 billion galaxies in the universe. The news of our cosmic unimportance triggers impressive defense mechanisms in the human psyche. Many of us unwittingly resemble the man in the cartoon who gazes at the starry heavens and remarks to his companion, "When I look at all those stars, I'm struck by how insignificant they are." Throughout history, different cultures have produced creation myths that explain our origins as the result of cosmic forces shaping our destiny. These histories have helped us to ward off feelings of insignificance. Although origin stories typically begin with the big picture, they get down to earth with impressive speed, zipping past the creation of the universe, of all its contents, and of life on Earth, to arrive at long explanations of myriad details of human history and its social conflicts. As if we somehow formed the center of creation. Almost all the disparate answers to the quest of origins accept as their underlying premise that the cosmos behaves in accordance with general rules, which reveal themselves, at least in principle, to our careful examination of the world around us. Ancient Greek philosophers raised this premise to exalted heights, insisting that we humans possess the power to perceive how nature operates, as well as the underlying reality beneath what we observe, the fundamental truths that govern all else. Quite understandably, they insisted that uncovering those truths would be difficult. 2,300 years ago, in his most famous reflection on our ignorance, the Greek philosopher Plato compared those who strive for knowledge to prisoners chained in a cave, unable to see objects behind them, and who must attempt to deduce from the shadows of these objects an accurate description of reality. With this simile, Plato not only summarized humanity's attempts to understand the cosmos but also emphasized that we have a natural tendency to believe that mysterious, dimly sensed entities govern the universe, privy to knowledge that we can, at best, glimpse only in part. From Plato to Buddha, from Moses to Muhammad, from a hypothesized cosmic creator to modern films about the Matrix, humans in every culture have concluded that higher powers rule the cosmos, gifted with an understanding of the gulf between reality and superficial appearance. Half a millennium ago, a new approach toward understanding nature slowly took hold. This attitude, which we now call science, arose from the confluence of new technologies and the discoveries that they fostered. The spread of printed books across Europe, together with simultaneous improvements in travel by road and water, allowed individuals to communicate more quickly and effectively, so that they could learn what others had to say and could respond far more rapidly than in the past. During the 16th and 17th centuries, this hastened back and forth disputation and led to a new way of acquiring knowledge, based on the principle that the most effective means of understanding the cosmos relies on careful observations, coupled with attempts to specify broad and basic principles that explain a set of these observations. One more concept gave birth to science. Science depends on organized skepticism, that is, on continual, methodical doubting. Few of us doubt our own conclusions, so science embraces its skeptical approach by rewarding those who doubt someone else's. We may rightly call this approach unnatural, not so much because it calls for mistrusting someone else's thoughts, but because science encourages and rewards those who can demonstrate that another scientist's conclusions are just plain wrong. To other scientists, the scientist who corrects a colleague's error, or cites good reasons for seriously doubting his or her conclusions, performs a noble deed, like a Zen master who boxes the ears of a novice straying from the meditative path. Although scientists correct one another more as equals than as master and student. By rewarding a scientist who spots another's errors, a task that human nature makes much easier than discerning one's own mistakes, scientists as a group have created an inborn system of self-correction. Scientists have collectively created our most efficient and effective tool for analyzing nature, because they seek to disprove other scientists' theories even as they support their earnest attempts to advance human knowledge. Science thus amounts to a collective pursuit, but a mutual admiration society it is not, nor was meant to be. Like all attempts at human progress, the scientific approach works better in theory than in practice. Not all scientists doubt one another as effectively as they should. The need to impress scientists who occupy powerful positions, and who are sometimes swayed by factors that lie beyond their conscious knowledge, can interfere with science's self-correcting ability. In the long run, however, errors cannot endure, because other scientists will discover them and promote their own careers by trumpeting the news. Those conclusions that do survive the attacks of other scientists will eventually achieve the status of scientific laws, accepted as valid descriptions of reality, even though scientists understand that each of these laws may someday find itself to be only part of a larger, deeper truth. But scientists hardly spend all their time attempting to prove one another mistaken. Most scientific endeavors proceed by testing imperfectly established hypotheses against slightly improved observational results. Every once in a while, however, a significantly new take on an important theory emerges, or a whole new range of observations opens the way to a new set of hypotheses to explain these new results. The greatest moments in scientific history have arisen, and will always arise, when a new explanation, perhaps coupled with new observational results, produces a seismic shift in our conclusions about the workings of nature. Scientific progress depends on individuals in both camps, those who assemble better data and extrapolate carefully from it, and those who risk much, and have much to gain if successful, by challenging widely accepted conclusions. Science's skeptical core makes it a poor competitor for human hearts and minds, which recoil from its ongoing controversies and prefer the security of seemingly eternal truths. If the scientific approach were just one more interpretation of the cosmos, it would never have amounted to much, but science's big-time success rests on the fact that it works. If you board an aircraft built according to science, with principles that have survived numerous attempts to prove them wrong, you have a far better chance of reaching your destination than you do in an aircraft constructed by the rules of Vedic astrology. Throughout relatively recent history, people confronted with the success of science in explaining natural phenomena have reacted in one of four ways. First, a small minority have embraced the scientific method as our best hope for understanding nature, and seek no additional ways to comprehend the universe. Second, a much larger number ignore science, judging it uninteresting, opaque, or opposed to the human spirit. Third, another minority, conscious of the assault that science seems to make upon their cherished beliefs, seek actively to disprove scientific results that annoy or enrage them. They do so, however, quite outside the skeptical framework of science, as you can easily establish by asking one of them, what evidence would convince you that you are wrong? These anti-scientists still feel the shock that John Donne described in his poem, The Anatomy of the World. The first anniversary, written in 1611 as the first fruits of modern science appeared. And new philosophy calls all in doubt, the element of fire is quite put out, the sun is lost, and th earth, and no man's wit can well direct him where to look for it. And freely men confess that this world spent, when in the planets and the firmament they seek so many new, they see that this is crumbled out again to his atomies. 'Tis all in pieces, all coherence gone. Fourth, another large section of the public accepts the scientific approach to nature while maintaining a belief in supernatural entities existing beyond our complete understanding that rule the cosmos. Baruch Spinoza, the philosopher who created the strongest bridge between the natural and the supernatural, rejected any distinction between nature and God, insisting instead that the cosmos is simultaneously nature and God. Adherents of more conventional religions, which typically insist on this distinction, often reconcile the two by mentally separating the domains in which the natural and the supernatural operate. No matter what camp you may live in, no one doubts that these are auspicious times for learning what's new in the cosmos. Let us then proceed with our adventurous quest for cosmic origins, acting much like detectives who deduce the facts of the crime from the evidence left behind. We invite you to join us in search of cosmic clues, and the means of interpreting them, so that together we may uncover the story of how part of the universe turned into ourselves. Overture. The greatest story ever told. The world has persisted many a long year, having once been set going in the appropriate motions. From these everything else follows. Lucretius. Some 14 billion years ago, at the beginning of time, all the space and all the matter and all the energy of the known universe fit within a pinhead. The universe was then so hot that the basic forces of nature, which collectively describe the universe, were merged into a single, unified force. When the universe was a roaring 1030 degrees and just 10 to 43 seconds old, the time before which all of our theories of matter and space lose their meaning, black holes spontaneously formed, disappeared, and formed again out of the energy contained within the unified force field. Under these extreme conditions, in what is admittedly speculative physics, the structure of space and time became severely curved as it gurgled into a spongy, foam-like structure. During this epoch, phenomena described by Einstein's general theory of relativity and quantum mechanics were indistinguishable. As the universe expanded and cooled, gravity split from the other forces. Soon thereafter, the strong nuclear force and the electroweak force split from each other, an event accompanied by an enormous release of stored energy that induced a rapid, 50^10 increase in the size of the universe. The rapid expansion, known as the epoch of inflation, stretched and smoothed matter and energy so that any variation in density from one part of the universe to the next became less than 1 part in 100,000. Continuing onward with what is now laboratory-confirmed physics, the universe was hot enough for photons to spontaneously convert their energy into matter-antimatter particle pairs, which immediately thereafter annihilated each other, returning their energy back to photons. For reasons unknown, this symmetry between matter and antimatter had been broken at the previous force splitting, which led to a slight excess of matter over antimatter. The asymmetry was small but crucial for the future evolution of the universe. For every 1 billion antimatter particles, 1 billion plus 1 matter particles were born. As the universe continued to cool, the electroweak force split into the electromagnetic force and the weak nuclear force, completing the four distinct and familiar forces of nature. While the energy of the photon bath continued to drop, pairs of matter-antimatter particles could no longer be created spontaneously from the available photons. All remaining pairs of matter-antimatter particles swiftly annihilated, leaving behind a universe with one particle of ordinary matter for every billion photons. And no antimatter. Had this matter-over-antimatter asymmetry not emerged, the expanding universe would forever be composed of light and nothing else, not even astrophysicists. Over a roughly 3-minute period, the matter became protons and neutrons, many of which combined to become the simplest atomic nuclei. Meanwhile, free-roving electrons thoroughly scattered the photons to and fro, creating an opaque soup of matter and energy. When the universe cooled below a few thousand degrees Kelvin, somewhat hotter than a blast furnace, the loose electrons moved slowly enough to get snatched from the soup by the roving nuclei. To make complete atoms of hydrogen, helium, and lithium, the three lightest elements. The universe had now become transparent to visible light, and these free-flying photons are observable today as the cosmic microwave background. During its first billion years, the universe continued to expand and cool as matter gravitated into the massive concentrations we call galaxies. Within just the volume of the cosmos that we can see, 100 billion of these galaxies formed, each containing hundreds of billions of stars that undergo thermonuclear fusion in their cores. Those stars with more than about 10 times the mass of the Sun achieve sufficient pressure and temperature in their cores to manufacture dozens of elements heavier than hydrogen, including the elements that compose planets and the life upon them. These elements would be embarrassingly useless were they to remain locked inside the star. But high-mass stars explode in death, scattering their chemically enriched guts throughout the galaxy. After 7 or 8 billion years of such enrichment, an undistinguished star was born in an undistinguished region of an undistinguished galaxy in an undistinguished part of the universe. The gas cloud from which the Sun formed contained a sufficient supply of heavy elements to spawn a few planets, thousands of asteroids, and billions of comets. During the formation of this star system, matter condensed and accreted out of the parent cloud of gas while circling the Sun. For several 100 million years, the persistent impacts of high-velocity comets and other leftover debris rendered molten the surfaces of the rocky planets, preventing the formation of complex molecules. As less and less accretable matter remained in the solar system, the planet's surfaces began to cool. The planet we call Earth formed in an orbit where its atmosphere can sustain oceans, largely in liquid form. Had Earth formed much closer to the Sun, the oceans would have vaporized. Had Earth formed much farther, the oceans would have frozen. In either case, life as we know it would not have evolved. Within the chemically rich liquid oceans, by a mechanism unknown, simple anaerobic bacteria emerged that unwittingly transformed Earth's carbon dioxide, rich atmosphere into one with sufficient oxygen to allow aerobic organisms to form, evolve, and dominate the oceans and land. These same oxygen atoms, normally found in pairs, also combined in threes to form ozone in the upper atmosphere, which shields Earth's surface from most of the Sun's molecule-hostile ultraviolet photons. The remarkable diversity of life on Earth, and elsewhere in the universe, arises from the cosmic abundance of carbon and the countless number of molecules made from it. More varieties of carbon-based molecules exist than of all other molecules combined. But life is fragile. Earth's encounters with large objects, left over from the formation of the solar system, which were once common events, still wreak intermittent havoc upon our ecosystem. A mere 65 million years ago, a 10 trillion-ton asteroid struck what is now the Yucatan Peninsula and obliterated over 70% of Earth's land-based flora and fauna, including all the dinosaurs, the dominant land animals of that epoch. This ecological tragedy opened an opportunity for small, surviving mammals to fill freshly vacant niches. A big-brained branch of these mammals, one we call primates, evolved a genus and species, Homo sapiens, to a level of intelligence that enabled them to invent methods and tools of science, to invent astrophysics, and to deduce the origin and evolution of the universe. Yes, the universe had a beginning. Yes, the universe continues to evolve. And yes, every one of our body's atoms is traceable to the Big Bang and to the thermonuclear furnaces within high-mass stars. We are not simply in the universe, we are part of it. We are born from it. One might even say that the universe has empowered us, here in our small corner of the cosmos, to figure itself out. And we have only just begun. Part 1. The origin of the universe. In the beginning. In the beginning, there was physics. Physics describes how matter, energy, space, and time behave and interact with one another. The interplay of these characters in our cosmic drama underlies all biological and chemical phenomena. Hence everything fundamental and familiar to us earthlings begins with, and rests upon, the laws of physics. When we apply these laws to astronomical settings, we deal with physics writ large, which we call astrophysics. In almost any area of scientific inquiry, but especially in physics, the frontier of discovery lives at the extremes of our ability to measure events and situations. In an extreme of matter, such as the neighborhood of a black hole, gravity strongly warps the surrounding space-time continuum. At an extreme of energy, thermonuclear fusion sustains itself within the 15 million degree cores of stars. And at every extreme imaginable we find the outrageously hot and dense conditions that prevailed during the first few moments of the universe. To understand what happens in each of these scenarios requires laws of physics discovered after 1900, during what physicists now call the modern era, to distinguish it from the classical era that includes all previous physics. One major feature of classical physics is that events and laws and predictions actually make sense when you stop and think about them. They were all discovered and tested in ordinary laboratories in ordinary buildings. The laws of gravity and motion, of electricity and magnetism, and of the nature and behavior of heat energy are still taught in high school physics classes. These revelations about the natural world fueled the Industrial Revolution, itself transforming culture and society in ways unimagined by generations that came before, and remain central to what happens, and why, in the world of everyday experience. By contrast, nothing makes sense in modern physics because everything happens in regimes that lie far beyond those to which our human senses respond. This is a good thing. We may happily report that our daily lives remain wholly devoid of extreme physics. On a normal morning, you get out of bed, wander around the house, eat something, then dash out the front door. At day's end, your loved ones fully expect you to look no different than you did when you left, and to return home in one piece. But imagine yourself arriving at the office, walking into an overheated conference room for an important 10 a.m. meeting, and suddenly losing all your electrons, or worse yet, having every atom of your body fly apart. That would be bad. Suppose instead that you're sitting in your office trying to get some work done by the light of your 75-watt desk lamp, when somebody flicks on 500 watts of overhead lights, causing your body to bounce randomly from wall to wall until you're jack-in-the-boxed out the window. Or what if you go to a sumo wrestling match after work, only to see the two nearly spherical gentlemen collide, disappear, and then spontaneously become two beams of light that leave the room in opposite directions? Or suppose that on your way home, you take a road less traveled, and a darkened building sucks you in feet first, stretching your body head to toe while squeezing you shoulder to shoulder as you get extruded through a hole, never to be seen or heard from again. If those scenes played themselves out in our daily lives, we would find modern physics far less bizarre. Our knowledge of the foundations of relativity and quantum mechanics would flow naturally from our life experiences, and our loved ones would probably never let us go to work. But back in the early minutes of the universe, that kind of stuff happened all the time. To envision it, and to understand it, we have no choice but to establish a new form of common sense, an altered intuition about how matter behaves, and how physical laws describe its behavior, at extremes of temperature, density, and pressure. We must enter the world of E equals mc squared. Albert Einstein first published a version of this famous equation in 1905, the year in which his seminal research paper entitled Zur Elektrodynamik bewegter Körper appeared in Annalen der Physik, the preeminent German journal of physics. The paper's title in English reads, On the Electrodynamics of Moving Bodies, but the work is far better known as Einstein's special theory of relativity, which introduced concepts that forever changed our notions of space and time. Just 26 years old in 1905, working as a patent examiner in Bern, Switzerland, Einstein offered further details, including his best-known equation in another, remarkably short paper published later the same year in the same journal. Ist die Trägheit eines Körpers von seinem Energieinhalt abhängig, or does the inertia of a body depend on its energy content? To save you the effort of locating the original article, of designing an experiment, and of thus testing Einstein's theory, the answer to the paper's title is yes. As Einstein wrote, if a body gives off the energy E in the form of radiation, its mass diminishes by EC2. The mass of a body is a measure of its energy content. If the energy changes by E, the mass changes in the same sense. Uncertain as to the truth of his statement, he then suggested, it is not impossible that with bodies whose energy content is variable to a high degree the theory may be successfully put to the test. There you have it, the algebraic recipe for all occasions when you want to convert matter into energy or energy into matter. E equals mc squared, energy equals mass times the square of the speed of light, gives us a supremely powerful computational tool that extends our capacity to know and understand the universe from as it is now, all the way back to infinitesimal fractions of a second after the birth of the cosmos. With this equation, you can tell how much radiant energy a star can produce, or how much you could gain by converting the coins in your pocket into useful forms of energy. The most familiar form of energy, shining all around us, though often unrecognized and unnamed in our mind's eye, is the photon, a massless, irreducible particle of visible light, or of any other form of electromagnetic radiation. We all live within a continuous bath of photons, from the sun, the moon, and the stars, from your stove, your chandelier, and your nightlight, from hundreds of radio and television stations, and from countless cell phone and radar transmissions. Why, then, don't we actually see the daily transmuting of energy into matter, or of matter into energy? The energy of common photons sits far below the mass of the least massive subatomic particles, when converted into energy by E equals mc squared. Because these photons wield too little energy to become anything else, they lead simple, relatively uneventful lives. Do you long for some action with E equals mc squared? Start hanging around gamma-ray photons that have some real energy, at least 200,000 times more than visible photons. You'll quickly get sick and die of cancer, but before that happens, you'll see pairs of electrons, one made of matter, the other of antimatter, pop into existence where photons once roamed. As you watch, you'll also see matter-antimatter pairs of electrons collide, annihilating each other and creating gamma-ray photons once again. Increase the photon's energy by another factor of 2000, and you now have gamma rays with enough energy to turn susceptible people into the Hulk. Pairs of these photons wield enough energy, fully described by the power of E equals mc squared, to create particles such as neutrons, protons, and their antimatter partners, each nearly 2,000 times the mass of an electron. High-energy photons don't hang out just anywhere, but they do exist in many a cosmic crucible. For gamma rays, almost any environment hotter than a few billion degrees will do just fine. The cosmological significance of particles and energy packets that transform themselves into one another is staggering. Currently, the temperature of our expanding universe, found by measuring the bath of microwave photons that pervades all of space, is a mere 2.73 Kelvin. Like the photons of visible light, microwave photons are too cool to have any realistic ambitions of turning themselves into particles via E equals mc squared. In other words, no known particle has a mass so low that it can be made from the meager energy of a microwave photon. The same holds true for the photons that form radio waves, infrared, and visible light, as well as ultraviolet and X-rays. More simply expressed, particle transmutations all require gamma rays. Yesterday, however, the universe was a little bit smaller and a little bit hotter than today. The day before, it was smaller and hotter still. Roll the clocks backward some more, say, 13.7 billion years, and you land squarely in the post-Big Bang primordial soup, a time when the temperature of the cosmos was high enough to be astrophysically interesting as gamma rays filled the universe. To understand the behavior of space, time, matter, and energy from the Big Bang to present day is one of the greatest triumphs of human thought. If you seek a complete explanation for the events of the earliest moments, when the universe was smaller and hotter than ever thereafter, you must find a way to enable the four known forces of nature, gravity, electromagnetism, the strong and the weak nuclear forces, to talk to one another. To unify and become a single metaforce. You must also find a way to reconcile two currently incompatible branches of physics, quantum mechanics and general relativity. Spurred by the successful marriage of quantum mechanics and electromagnetism during the mid-20th century, physicists moved swiftly to blend quantum mechanics and general relativity into a single and coherent theory of quantum gravity. Although so far they have all failed, we already know where the high hurdles lie, during the Planck era. That's the cosmic phase up to 10 to 43 seconds after the beginning. Because information can never travel more rapidly than the speed of light, 3 by 108 meters per second, a hypothetical observer situated anywhere in the universe during the Planck era could see no farther than 3x 10 to 35 meter. The German physicist Max Planck, after whom these unimaginably small times and distances are named, introduced the idea of quantized energy in 1900 and generally receives credit as the father of quantum mechanics. Not to worry, though, so far as daily life goes. The clash between quantum mechanics and gravity poses no practical problem for the contemporary universe. Astrophysicists apply the tenets and tools of general relativity and quantum mechanics to extremely different classes of problems. But in the beginning, during the Planck era, the large was small, so there must have been a kind of shotgun wedding between the two. Alas, the vows exchanged during that ceremony continue to elude us, so no laws of physics describe with any confidence how the universe behaved during the brief honeymoon, before the expanding universe forced the very large and very small to part ways. At the end of the Planck era, gravity wriggled itself loose from the other, still unified forces of nature, achieving an independent identity nicely described by our current theories. As the universe aged past 10 to 35 seconds, it continued to expand and to cool, and what remained of the once unified forces divided into the electroweak force and the strong nuclear force. Later still, the electroweak force split into the electromagnetic and the weak nuclear forces, laying bare four distinct and familiar forces, with the weak force controlling radioactive decay, the strong force binding together the particles in each atomic nucleus, the electromagnetic force holding atoms together in molecules, and gravity binding matter in bulk. By the time the universe aged a trillionth of a second, its transmogrified forces, along with other critical episodes, had already imbued the cosmos with its fundamental properties, each worthy of its own book. While time dragged on for the universe's first trillionth of a second, the interplay of matter and energy continued incessantly. Shortly before, during, and after the strong and electroweak forces had split, the universe contained a seething ocean of quarks, leptons, and their antimatter siblings, along with bosons, the particles that enable these particles to interact with one another. None of these particle families, so far as we now know, can be divided into anything smaller or more basic. Fundamental though they are, each family of particles comes in several species. Photons, including those that form visible light, belong to the boson family. The leptons most familiar to the non-physicist are electrons and neutrinos, and the most familiar quarks are. Well, there are no familiar quarks, because in ordinary life we always find quarks bound together into particles such as protons and neutrons. Each species of quark has been assigned an abstract name that serves no real philological, philosophical, or pedagogical purpose except to distinguish it from the others, up and down, strange and charmed, and top and bottom. Bosons, by the way, derive their name from the Indian physicist Satyendranath Bose. The word lepton comes from the Greek leptos, meaning light or small. Quark, however, has a literary and far more imaginative origin. The American physicist Murray Gell-Mann, who in 1964 proposed the existence of quarks, and who then thought that the quark family had only 3 members, drew the Name from a characteristically elusive line in James Joyce's Finnegan's Wake, 3 quarks for muster mark. One advantage quarks can claim, all their names are simple, something that chemists, biologists, and geologists seem unable to achieve in naming their own stuff. Quarks are quirky. Unlike protons, which each have an electric charge of +1, and electrons, each with a charge of 1, quarks have fractional charges that come in units of 1/3. And except under the most extreme conditions, you'll never catch a quark all by itself, it will always be clutching on to 1 or 2 other quarks. In fact, the force that keeps 2 of them together actually grows stronger as you separate them, as if some sort of subnuclear rubber band held them together. Separate the quark sufficiently far, and the rubber band snaps. The energy stored in the stretched band now summons E=mc² to create a new quark at each end, leaving you back where you started. During the quark-lepton era in the cosmos's first trillionth of a second, the universe had a density sufficient for the average separation between unattached quarks to rival the separation between attached quarks. Under those conditions, allegiances between adjacent quarks could not be established unambiguously, so they moved freely among themselves. The experimental detection of this state of matter, understandably named quark soup, was reported for the first time in 2002 by a team of physicists working at the Brookhaven National Laboratories on Long Island. The combination of observation and theory suggests that an episode in the very early universe, perhaps during one of the splits between different types of force, endowed the cosmos with a remarkable asymmetry, in which particles of matter outnumbered particles of antimatter by only about 1 part in a billion, a difference that allows us to exist today. That tiny discrepancy in population could hardly have been noticed amid the continuous creation, annihilation, and recreation of quarks and antiquarks, electrons and anti-electrons, and neutrinos and antineutrinos. During that era, the odd man out, the slight preponderance of matter over antimatter, had plenty of opportunities to find other particles with which to annihilate, and so did all the other particles. But not for much longer. As the universe continued to expand and cool, its temperature fell rapidly below 1 trillion Kelvin. A millionth of a second had now passed since the beginning, but this tepid universe no longer had a temperature or density sufficient to cook quarks. All the quarks quickly grabbed dance partners, creating a permanent new family of heavy particles called hadrons. That quark-to-hadron transition quickly produced protons and neutrons as well as other, less familiar types of heavy particles, all composed of various combinations of quarks. The slight matter-antimatter asymmetry in the quark-lepton soup now passed to the hadrons, with extraordinary consequences. As the universe cooled, the amount of energy available for the spontaneous creation of particles declined continuously. During the hadron era, photons could no longer invoke E=mc² to manufacture quark-antiquark pairs. Their E could not cover the pairs mc2. In addition, the photons that emerged from all the remaining annihilations continued to lose energy to the ever-expanding universe, so their energies eventually fell below the threshold required to create hadron-antihadron pairs. Every billion annihilations left a billion photons in their wake, and only a single hadron survived, mute testimony to the tiny excess of matter over antimatter in the early universe. Those lone hadrons would ultimately get to have all the fun that matter can enjoy. They would provide the source of galaxies, stars, planets, and people. Without the imbalance of a billion and 1 to a mere billion between matter and antimatter particles, all the mass in the universe would have annihilated before the universe's first second had passed. Leaving a cosmos in which we could see photons and nothing else, the ultimate let-there-be-light scenario. By now, 1 second of time has passed. At 1 billion degrees, the universe remains piping hot, still able to cook electrons, which, along with their positron counterparts, continue to pop in and out of existence. But within the ever-expanding, ever-cooling universe, their days are numbered. What was formerly true for hadrons now comes true for electrons and positrons. They annihilate each other, and only 1 electron in a billion emerges, the lone survivor of the matter-antimatter suicide pact. The other electrons and positrons died to flood the universe with a greater sea of photons. With the era of electron-positron annihilation over, the cosmos has frozen into existence one electron for every proton. As the cosmos continues to cool, with its temperature falling below 100 million degrees, its protons fuse with other protons and with neutrons, forming atomic nuclei and hatching a universe in which 90% of these nuclei are hydrogen and 10% are helium. Along with relatively tiny numbers of deuterium, tritium, and lithium nuclei. 2 minutes have now passed since the beginning. Not for another 380,000 years does much happen to our particle soup of hydrogen nuclei, helium nuclei, electrons, and photons. Throughout these hundreds of millennia, the cosmic temperature remains sufficiently hot for the electrons to roam free among the photons, batting them to and fro. As we will shortly detail in Chapter 3, this freedom comes to an abrupt end when the temperature of the universe falls below 3000 Kelvin. Right about now, all the electrons acquire orbits around the nuclei, forming atoms. The marriage of electrons with nuclei leaves the newly formed atoms within a ubiquitous bath of visible light photons, completing the story of how particles and atoms formed in the primordial universe. As the universe continues to expand, its photons continue to lose energy. Today, in every direction astrophysicists look, they find a cosmic fingerprint of microwave photons at a temperature of 273 degrees, which represents a 1,000-fold decline in the photon's energies since the time atoms first formed. The photons' patterns on the sky, the exact amount of energy that arrives from different directions, retain a memory of the cosmic distribution of matter just before atoms formed. From these patterns, astrophysicists can obtain remarkable knowledge, including the age and shape of the universe. Even though atoms now form part of daily life in the universe, Einstein's equation still has plenty of work to do, in particle accelerators, where matter-antimatter particle pairs are created routinely from energy fields, in the core of the Sun, where 4 million tons of matter are converted into energy every second, and in the cores of all other stars. E equals mc squared also manages to apply itself near black holes, just outside their event horizons, where particle-antiparticle pairs can pop into existence at the expense of the black hole's formidable gravitational energy. The British cosmologist Stephen Hawking first described the hijinks in 1975, showing that the entire mass of a black hole can slowly evaporate by this mechanism. In other words, black holes are not entirely black. The phenomenon is known as Hawking radiation, and serves as a reminder of the continued fertility of Einstein's most famous equation. But what happened before all this cosmic fury? What happened before the beginning? Astrophysicists have no idea. Rather, our most creative ideas have little or no grounding in experimental science. Yet the religious faithful tend to assert, often with a tinge of smugness, that something must have started it all, a force greater than all others, a source from which everything issues. A prime mover. In the mind of such a person that something is, of course, God, whose nature varies from believer to believer but who always bears the responsibility for starting the ball rolling. But what if the universe was always there, in a state or condition that we have yet to identify, a multiverse, for example, in which everything we call the universe amounts to only a tiny bubble in an ocean of suds? Or what if the universe, like its particles, just popped into existence from nothing we could see? These rejoinders typically satisfy no one. Nonetheless, they remind us that informed ignorance provides the natural state of mind for research scientists at the ever-shifting frontiers of knowledge. People who believe themselves ignorant of nothing have neither looked for, nor stumbled upon, the boundary between what is known and unknown in the cosmos. And therein lies a fascinating dichotomy. The universe always was, gets no respect as a legitimate answer to what was around before the beginning. But for many religious people, the answer, God always was, is the obvious and pleasing answer to what was around before God. No matter who you may be, engaging yourself in the quest to discover where and how everything began can induce emotional fervor, as if knowing our beginnings would bestow upon you some form of fellowship with, or perhaps governance over, all that comes later. So what is true for life itself is true for the universe. Knowing where you came from is no less important than knowing where you are going. Antimatter matters. particle physicists have won the contest for the most peculiar, yet playful jargon of all the physical sciences. Where else could you find a neutral vector boson exchanged between a negative muon and a muon neutrino? Or a gluon exchange binding together a strange quark and a charmed quark? And where else can you meet squarks, photinos, and gravitinos? Alongside these seemingly countless particles with peculiar names, particle physicists must contend with a parallel universe of antiparticles, collectively known as antimatter. Despite its persistent appearance in science fiction stories, antimatter is real. And as you might suppose, it does tend to annihilate upon contact with ordinary matter. The universe reveals a peculiar romance between antiparticles and particles. They can be born together out of pure energy, and they can annihilate as they reconvert their combined mass back into energy. In 1932, the American physicist Carl David Anderson discovered the anti-electron, the positively charged, antimatter counterpart to the negatively charged electron. Since then, particle physicists have routinely made antiparticles of all varieties in the world's particle accelerators, but only recently have they assembled antiparticles into whole atoms. Since 1996, an international group led by Walter Ohlert of the Institute for Nuclear Physics Research in Jülich, Germany, has created atoms of antihydrogen, in which an anti-electron happily orbits an antiproton. To make these first anti-atoms, the physicists used the giant particle accelerator operated by the European Organization for Nuclear Research in Geneva, Switzerland, where so many important contributions to particle physics have occurred. The physicists use a simple creation method, make a bunch of anti-electrons and a bunch of antiprotons, bring them together at a suitable temperature and density, and wait for them to combine to form atoms. During their first round of experiments, Ohlert's team produced 9 atoms of antihydrogen. But in a world dominated by ordinary matter, life as an antimatter atom can be precarious. The antihydrogen atoms survived for less than 40 nanoseconds before annihilating with ordinary atoms. The discovery of the anti-electron was one of the great triumphs of theoretical physics, for its existence had been predicted just a few years earlier by the British-born physicist Paul A. M. Dirac. To describe matter on the smallest size scales, those of atomic and subatomic particles, physicists developed a new branch of physics during the 1920s to explain the results of their experiments with these particles. Using newly established rules, now known as quantum theory, Dirac postulated from a second solution to his equation that a phantom electron from the other side might occasionally pop into the world as an ordinary electron, leaving behind a gap or hole in the sea of negative energies. Although Dirac hoped to explain protons in this way, other physicists suggested that this hole would reveal itself experimentally as a positively charged anti-electron, which had come to be known as a positron for its positive electric charge. The detection of actual positrons confirmed Dirac's basic insight and established antimatter as worthy of as much respect as matter. Equations with double solutions are not unusual. One of the simplest examples answers the question, what number times itself equals 9? Is it 3 or 3? Of course, the answer is both, because 3 times 3 is equal to 9 and 3x, 3 is equal to 9. Physicists cannot guarantee that all the solutions of an equation correspond to events in the real world, but if a mathematical model of a physical phenomenon is correct, manipulating its equations can be as useful as manipulating the entire universe. As with Dirac and antimatter, such steps often lead to verifiable predictions. If the predictions prove incorrect, then the theory is discarded. But regardless of the physical outcome, a mathematical model ensures that the conclusions you may draw from it are both logical and internally consistent. Subatomic particles have many measurable features, of which mass and electric charge rank among the most important. Except for the particle's mass, which is always the same for a particle and its antiparticle, the specific properties of each type of antiparticle will always be precisely opposite to those of the particle for which it provides the anti. For example, the positron has the same mass as the electron, but the positron has 1 unit of positive charge while the electron has 1 unit of negative charge. Similarly, the antiproton provides the oppositely charged antiparticle of the proton. Believe it or not, the chargeless neutron also has an antiparticle. It's called, you guessed it, the antineutron. An antineutron has an opposite zero charge with respect to the ordinary neutron. This arithmetical magic derives from the particular triplet of fractionally charged particles that form neutrons. The three quarks that compose a neutron have charges of and plus, while those in the antineutron have charges of and. Each set of three quark charges adds up to zero net charge, yet the corresponding components do have opposite charges. Antimatter can pop into existence out of thin air. If gamma-ray photons have sufficiently high energy, they can transform themselves into electron-positron pairs, thus converting all of their seriously large energy into a small amount of matter, in a process whose energy side fulfills Einstein's famous equation E equals mc squared. In the language of Dirac's original interpretation, the gamma-ray photon kicked an electron out of the domain of negative energies, creating an ordinary electron and an electron hole. The reverse process can also occur. If a particle and an antiparticle collide, they will annihilate by refilling the hole and emitting gamma rays. Gamma rays are the sort of radiation you should avoid. If you somehow manage to manufacture a blob of antiparticles at home, you have a wolf by the ears. Storage would immediately become a challenge, because your antiparticles would annihilate with any conventional sack or grocery bag in which you chose to confine or carry them. A cleverer storage mechanism involves trapping the charged antiparticles within the confines of a strong magnetic field, where they are repelled by invisible but highly effective magnetic walls. If you embed the magnetic field in a vacuum, you can render the antiparticles safe from annihilation with ordinary matter. This magnetic equivalent of a bottle will also be the bag of choice whenever you must handle other container-hostile materials, such as the 100 million degree glowing gases involved in nuclear fusion experiments. The greatest storage problem arises after you have created entire antiatoms, because antiatoms, like atoms, do not normally rebound from a magnetic wall. You would be wise to keep your positrons and antiprotons in separate magnetic bottles until you must. To generate antimatter requires at least as much energy as you can recover when it annihilates with matter to become energy again. Unless you had a full tank of antimatter fuel before launch, a self-generating antimatter engine would slowly suck energy from your starship. Perhaps the original Star Trek television and film series embodied this fact, but if memory serves, Captain Kirk continually asked for more power from the matter-antimatter drives, and Scotty invariably replied in his Scottish accent that, the engines canna take it. Although physicists expect hydrogen and antihydrogen atoms to behave identically, they have not yet verified this prediction experimentally, mainly because of the difficulty they face in keeping antihydrogen atoms in existence. Rather than having them annihilate almost immediately with protons and electrons, they would like to verify that the detailed behavior of a positron bound to an antiproton in an antihydrogen atom obeys all the laws of quantum theory, and that an antiatom's gravity behaves precisely as we expect of ordinary atoms. Could an antiatom produce antigravity instead of ordinary gravity? All theory points toward the latter, but the former, if it should prove correct, would offer amazing new insights into nature. On atomic-size scales, the force of gravity between any two particles is immeasurably small. Instead of gravity, electromagnetic and nuclear forces dominate the behavior of these tiny particles, because both forces are much, much stronger than gravity. To test for anti-gravity, you would need enough antiatoms to make ordinary-sized objects, so that you can measure their bulk properties and compare them to ordinary matter. If a set of billiard balls were made of antimatter, would a game of anti-pool be indistinguishable from a game of pool? Would an anti-8 ball fall into the corner pocket in exactly the same way as an ordinary 8 ball? Would antiplanets orbit an anti-star the way that ordinary planets orbit ordinary stars? It's philosophically sensible, and in line with all the predictions of modern physics, to presume that the bulk properties of antimatter will prove to be identical to those of ordinary matter, normal gravity, normal collisions, normal light, and so forth. Unfortunately, this means that if an anti-galaxy were headed our way, on a collision course with the Milky Way, it would remain indistinguishable from an ordinary galaxy until it was too late to do anything about it. But this fearsome fate cannot be common in the universe today because if, for example, a single anti-star annihilated with a single ordinary star, the conversion of their matter and antimatter into gamma-ray energy would be swift, violent, and total. If two stars with masses similar to the Sun's were to collide in our galaxy, their melding would produce an object so luminous that it would temporarily outproduce all the energy of all the stars of 100 million galaxies and ferry us to an untimely end. We have no compelling evidence that such an event has ever occurred anywhere in the universe. So, best we can judge, the universe is dominated by ordinary matter, and has been since the first few minutes after the Big Bang. Thus total annihilation through matter-antimatter collisions need not rank among your chief safety concerns on your next intergalactic voyage. Still, the universe now seems disturbingly imbalanced. We expect particles and antiparticles to be created in equal numbers, yet we find a cosmos dominated by ordinary particles, which seem to be perfectly happy without their antiparticles. Do hidden pockets of antimatter in the universe account for the imbalance? Was a law of physics violated during the early universe, forever tipping the balance in favor of matter over antimatter? We may never know the answers to these questions, but for now, if an alien hovers over your front lawn and extends an appendage as a gesture of greeting, toss it your 8-ball before you get too friendly. If the appendage and the ball explode, the alien probably consists of antimatter. And if nothing untoward occurs, you can proceed safely to take your new friend to your leader. Let there be light. At the time when the universe was just a fraction of a second old, a ferocious trillion degrees hot, and aglow with an unimaginable brilliance, its main agenda was expansion. With every passing moment the universe got bigger as more space came into existence from nothing. As the universe expanded, it grew cooler and dimmer. For hundreds of millennia, matter and energy cohabited in a kind of thick soup in which speedy electrons continually scattered photons of light to and fro. Back then, if your mission had been to see across the universe, you couldn't have done so. Any photons entering your eye would, just nanoseconds or picoseconds earlier, have bounced off electrons right in front of your face. You would have seen only a glowing fog in all directions, and your entire surroundings, luminous, translucent, reddish-white in color, would have been nearly as bright as the surface of the sun. As the universe expanded, the energy carried by each photon decreased. Eventually, about the time that the young universe reached its 380,000th birthday, its temperature dropped below 3,000 degrees, with the result that protons and helium nuclei could permanently capture electrons, thus bringing atoms into the universe. In previous epochs, every photon had sufficient energy to break apart a newly formed atom, but now the photons had lost this ability, thanks to the cosmic expansion. With fewer unattached electrons to gum up the works, the photons could finally race through space without bumping into anything. That's when the universe became transparent, the fog lifted, and a cosmic background of visible light was set free. That cosmic background persists to this day, the remnant of leftover light from a dazzling, sizzling early universe. It's a ubiquitous bath of photons, acting as much like waves as they do like particles. Each photon's wavelength equals the separation between one of its wiggly wave crests and the next, a distance you could measure with a ruler, if you could get your hands on a photon. All photons travel at the same speed in a vacuum, 186,000 miles per second, so photons with shorter wavelengths have a larger number of wave crests passing a particular point each second. Shorter wavelength photons therefore pack more wiggles into a given interval of time, so will have higher frequencies, more wiggles per second. Each photon's frequency provides a direct measure of its energy. The higher the photon frequency, the more energy that photon carries. As the cosmos cooled, photons lost energy to the expanding universe. The photons born in the gamma-ray and X-ray parts of the spectrum morphed into ultraviolet, visible light, and infrared photons. As their wavelengths grew larger, they became cooler and less energetic, but they never stopped being photons. Today, 13.7 billion years after the beginning, the photons of the cosmic background have shifted down the spectrum to become microwaves. That's why astrophysicists call it the cosmic microwave background, though a more enduring name is the cosmic background. Radiation, or CBR. 100 billion years from now, when the universe has expanded and cooled some more, future astrophysicists will describe the CBR as the cosmic radio wave background. The temperature of the universe drops as the size of the universe grows. It's a physical thing. As different parts of the universe move apart, the wavelengths of the photons in the CBR must increase. The cosmos stretches these waves within the spandex fabric of space and time. Because every photon's energy varies in inverse proportion to its wavelength, all the free-traveling photons will lose half their original energy for every doubling in size of the cosmos. All objects with temperatures above absolute zero will radiate photons throughout all parts of the spectrum. But that radiation always has a peak somewhere. The peak energy output of an ordinary household light bulb lies in the infrared part of the spectrum, which you can detect as warmth on your skin. Of course, light bulbs also emit plenty of visible light, or we wouldn't buy them. So you can feel a lamp's radiation as well as see it. The peak output of the cosmic background radiation occurs at a wavelength of about 1 millimeter, smack dab in the microwave part of the spectrum. The static that you hear on a walkie-talkie comes from an ambient bath of microwaves, a few % of which are from the CBR. The rest of the noise comes from the sun, cell phones, police radar guns, and so on. Besides peaking in the microwave region, the CBR also contains some radio waves and a vanishingly small number of photons with energies higher than those of microwaves. The Ukrainian-born American physicist George Gamow and his colleagues predicted the existence of the CBR during the 1940s, consolidating their efforts in a 1948 paper that applied the then-known laws of physics to the strange conditions of the early universe. The foundation for their ideas came from the 1927 paper by Georges-Édouard Lemaitre, a Belgian astronomer and Jesuit priest, now generally recognized as the father of Big Bang cosmology. But two U.S. physicists, Ralph Alpher and Robert Herman, who had previously collaborated with Gamow, first estimated what the temperature of the cosmic background ought to be. In hindsight, Alpher, Gamow, and Herman had what today seems a relatively simple argument, one which we have already made: the fabric of spacetime was smaller yesterday than it is today, and since it was smaller, basic physics requires that it was hotter. So the physicists turned back the clock to imagine the epoch we have described, the time when the universe was so hot that all its atomic nuclei were laid bare because photon collisions knocked all electrons loose to roam freely through space. Under those conditions, Alpher and Herman hypothesized, photons could not have sped uninterrupted across the universe, as they do today. The photon's current free ride requires that the cosmos grew sufficiently cool for the electrons to settle into orbits around the atomic nuclei. This formed complete atoms and allowed light to travel without obstruction. Although Gamow had the crucial insight that the early universe must have been much hotter than our universe today, Alpher and Herman were the first to calculate what its temperature would be today: 5 Kelvin. Yes, they got the number wrong. The CBR actually has a temperature of 2.73 Kelvin. But these three guys nevertheless performed a successful extrapolation back into the depths of long-vanished cosmic epochs, as great a feat as any other in the history of science. To take some basic atomic physics from a slab in the lab, and to deduce from it the largest scale phenomenon ever measured, the temperature history of our universe ranks as nothing short of mind-blowing. Assessing this accomplishment, J. Richard Guthrie, an astrophysicist at Princeton University, wrote in Time Travel in Einstein's Universe. Predicting that the radiation existed and then getting its temperature correct to within a factor of 2 was a remarkable accomplishment, rather like predicting that a flying saucer 50 feet in width would land on the White House lawn and then watching 127 feet in width actually show up. When Gamow, Alpher, and Herman made their predictions, physicists were still undecided about the story of how the universe began. In 1948, the same year that Alpher and Herman's paper appeared, a rival, steady-state, theory of the universe appeared in 2 papers published in England, one co-authored by the mathematician Hermann Bondi and the astrophysicist Thomas Gold, the other by the cosmologist Fred Hoyle. The steady-state theory requires that the universe, though expanding, has always looked the same, a hypothesis with a deeply attractive simplicity. But because the universe is expanding, and because a steady-state universe would not have been any hotter or denser yesterday than today, The Bondi-Goldhoyle scenario maintained that matter continuously pops into our universe at just the right rate to maintain a constant average density in the expanding cosmos. In contrast, the Big Bang theory requires that all matter come into existence at one instant, which some find more emotionally satisfying. Notice that the steady-state theory takes the issue of the origin of the universe and throws it backward an infinite distance in time. Highly convenient for those who would rather not examine this thorny problem. The prediction of the cosmic background radiation amounted to a shot across the bow of the steady-state theorists. The CBR's existence would clearly demonstrate that the universe was once far different, much smaller and hotter, from the way we find it today. The first direct observations of the CBR therefore put the first nails in the coffin of the steady-state theory. In 1964, the CBR was inadvertently and serendipitously discovered by Arno Penzias and Robert Wilson at the Bell Telephone Laboratories in Murray Hill, New Jersey. Little more than a decade later, Penzias and Wilson received the Nobel Prize for their good luck and hard work. What led Penzias and Wilson to their Nobel Prize? During the early 1960s, physicists all knew about microwaves, but almost no one had created the capability of detecting weak signals in the microwave portion of the spectrum. Back then, most wireless communication rode on radio waves, which have longer wavelengths than microwaves. For these, scientists needed a shorter wavelength detector and a sensitive antenna to capture them. Bell Labs had one, a king-size, horn-shaped antenna that could focus and detect microwaves as well as any apparatus on Earth. If you're going to send or receive a signal of any kind, you don't want other signals to contaminate it. Penzias and Wilson were trying to open up a new channel of communication for Bell Labs, so they wanted to pin down how much contaminating background interference these signals would experience, from the sun, from the center of the galaxy, from terrestrial sources, from whatever. They therefore embarked on a standard, important, and entirely innocent measurement, aimed at establishing how easily they could detect microwave signals. Though Penzias and Wilson had some astronomy background, they were not cosmologists but technophysicists studying microwaves, unaware of the predictions made by Gamow, Alpher, and Herman. What they were decidedly not looking for was the cosmic microwave background. So they ran their experiment, and corrected their data for all known sources of interference. But they found background noise in the signal that didn't go away, and they couldn't figure out how to get rid of it. The noise seemed to come from every direction above the horizon, and it didn't change with time. Finally they looked inside their giant horn. Pigeons were nesting there, leaving a white dielectric substance everywhere nearby. Things must have been getting desperate for Penzias and Wilson. Could the droppings, they wondered, be responsible for the background noise? They cleaned it up, and sure enough, the noise dropped a bit. But it still wouldn't go away. The paper they published in 1965 in the Astrophysical Journal refers to the persistent puzzle of an inexplicable, excess antenna temperature, rather than the astronomical discovery of the century. While Penzias and Wilson were scrubbing bird droppings from their antenna, a team of physicists at Princeton University led by Robert H. Dicke was building a detector specifically designed to find the CBR that Gamow, Alpher, and Herman had predicted. The professors, however, lacked the resources of Bell Labs, so their work proceeded more slowly. The moment that Dicke and his colleagues heard about Penzias and Wilson's results, they knew that they'd been scooped. The Princeton team knew exactly what the excess antenna temperature was. Everything fit the theory: the temperature, the fact that the signal came from all directions in equal amounts, and that it wasn't linked in time with Earth's rotation or Earth's position in orbit around the Sun. But why should anybody accept the interpretation? For good reason. Photons take time to reach us from distant parts of the cosmos, so we inevitably look back in time whenever we look outward into space. This means that if the intelligent inhabitants of a galaxy far, far away measured the temperature of the cosmic background radiation for themselves, long before we managed to so do, they should have found its temperature to be greater than 273 Kelvin, because they would have inhabited the universe when it was younger, smaller, and hotter than it is today. Can such an audacious assertion be tested? Yup. Turns out that the compound of carbon and nitrogen called cyanogen, best known to convicted murderers as the active ingredient of the gas administered by their executioners, will become excited by exposure to microwaves. If the microwaves are warmer than the ones in our CBR, they will excite the molecule a little more effectively than our microwaves do. The cyanogen compounds thus act as a cosmic thermometer. When we observe them in distant, and thus younger, galaxies, they should find themselves bathed in a warmer cosmic background than the cyanogen in our Milky Way galaxy. In other words, those galaxies ought to live more excited lives than we do. And they do. The spectrum of cyanogen in distant galaxies shows the microwaves to have just the temperature we expect at these earlier cosmic times. You can't make this stuff up. The CBR does far more for astrophysicists than to provide direct evidence for a hot early universe, and thus for the Big Bang model. It turns out that the details of the photons that comprise the CBR reach us laden with information about the cosmos both before and after the universe became transparent. We have noted that until that time, about 380,000 years after the Big Bang, the universe was opaque, so you couldn't have witnessed matter making shapes even if you'd been sitting front row center. You couldn't have seen where galaxy clusters were starting to form. Before anybody, anywhere, could see anything worth seeing, photons had to acquire the ability to travel, unimpeded, across the universe. When the time was right, each photon began its cross-cosmos journey at the point where it smacked into the last electron that would ever stand in its way. As more and more photons escaped without being deflected by electrons, they created an expanding shell of photons that astrophysicists call the surface of last scatter. That shell, which formed during a period of about 100,000 years, marks the epoch when almost all the atoms in the cosmos were born. By then, matter in large regions of the universe had already begun to coalesce. Where matter accumulates, gravity grows stronger, enabling more and more matter to gather. Those matter-rich regions seeded the formation of galaxy superclusters, while other regions remained relatively empty. The photons that last scattered off electrons within the coalescing regions developed a different, slightly cooler spectrum as they climbed out of the strengthening gravity field, which robbed them of a bit of energy. The CBR indeed shows spots that are slightly hotter or slightly cooler than average, typically by about 100,000th of a degree. These hot and cool spots mark the earliest structures in the cosmos, the first clumping together of matter. We know what matter looks like today because we see galaxies, galaxy clusters, and galaxy superclusters. To figure out how those systems arose, we probe the cosmic background radiation, a remarkable relic from the remote past, still filling the entire universe. Studying the patterns in the CBR amounts to a kind of cosmic phrenology. We can read the bumps on the skull of the youthful universe and from them deduce behavior not only for an infant but also for a grown-up. By adding other observations of the local and the distant universe, astronomers can determine all kinds of fundamental cosmic properties from the CBR. Compare the distribution of sizes and temperatures of the slightly warmer and cooler areas, for instance, and we can infer the strength of gravity in the early universe, and thus how quickly matter accumulated. From that we can then deduce how much ordinary matter, and dark energy the universe comprises. From there, it's easy to tell whether or not the universe will expand forever, and whether or not the expansion will slow down or speed up as time passes. Ordinary matter is what everyone is made of. It exerts gravity and can absorb, emit, and otherwise interact with light. Dark matter, as we'll see in Chapter 4, is a substance of unknown nature that produces gravity but does not interact with light in any known way. And dark energy, as we'll see in Chapter 5, induces an acceleration of the cosmic expansion, forcing the universe to expand more rapidly than it otherwise would. The phrenology exam now says that cosmologists understand how the early universe behaved, but that most of the universe, then and now, consists of stuff they're clueless about. Profound areas of ignorance notwithstanding, today, as never before, cosmology has an anchor. The CBR carries the imprint of a portal through which all of us once passed. Conclusion, originally derived from observations of distant galaxies, that the universe has been expanding for billions of years. It was the accurate and detailed map of the CBR, a map first made for small patches of the sky using balloon-borne instruments and a telescope at the South Pole. And then for the entire sky by a satellite called the Wilkinson Microwave Anisotropy Probe, that secured cosmology's place at the table of experimental science. We shall hear much more from WMAP, whose first results appeared in 2003, before our cosmological tale is done. Cosmologists have plenty of ego. How else could they have the audacity to deduce what brought the universe into being? But the new era of observational cosmology may call for a more modest, less freewheeling stance among its practitioners. Each new observation, each morsel of data, can be good or bad for your theories. On the one hand, the observations provide a basic foundation for cosmology, a foundation that so many other sciences can take for granted because they achieve rich streams of laboratory observations. On the other hand, new data will almost certainly dispatch some of the tall tales that theorists dreamed up when they lacked the observations that would give them thumbs up or down. No science achieves maturity without precision data. Cosmology has now become precision science. Let there be dark. Gravity, the most familiar of nature's forces, offers us simultaneously the best and the least understood phenomena in nature. It took the mind of Isaac Newton, the millennium's most brilliant and influential, to realize that gravity's mysterious action at a distance arises from the natural effects of every bit of matter, and that the attractive forces between any two objects can be described by a simple algebraic equation. It took the mind of Albert Einstein, the 20th century's most brilliant and influential, to show that we can more accurately describe gravity's action at a distance as a warp in the fabric of spacetime, produced by any combination of matter and energy. Einstein demonstrated that Newton's theory requires some modification to describe gravity accurately, in predicting, for example, the amount by which light rays will bend when they pass by a massive object. Although Einstein's equations are fancier than Newton's, they nicely accommodate the matter that we have come to know and love. Matter that we can see, touch, feel, and occasionally taste. Don't know who's next in the genius sequence, but we've now been waiting well over half a century for somebody to tell us why the bulk of all the gravitational forces that we've measured in the universe arises from substances that we have neither seen, nor touched, nor felt, nor tasted. Or maybe the excess gravity doesn't come from matter at all, but emanates from some other conceptual thing. In any case, we are without a clue. We find ourselves no closer to an answer today than we were when this missing mass problem was first identified in 1933 by astronomers who measured the velocities of galaxies whose gravity affects their close neighbors. And more fully analyzed in 1937 by the colorful Bulgarian-Swiss-American astrophysicist Fritz Zwicky, who taught at the California Institute of Technology for more than 40 years. Combining his far-ranging insights into the cosmos with a colorful means of expression and an impressive ability to antagonize his colleagues. Zwicky studied the movement of galaxies within a titanic cluster of galaxies, located far beyond the local stars of the Milky Way that trace out the constellation Coma Berenices. The Coma Cluster, as it is called by those in the know, is an isolated and richly populated ensemble of galaxies about 300 million light-years from Earth. Its many thousands of galaxies orbit the cluster's center, moving in all directions like bees circling their hive. Using the motions of a few dozen galaxies as tracers of the gravity field that binds the entire cluster, Zwicky discovered their average velocity to be shockingly high. Since larger gravitational forces induce higher velocities in the objects that they attract, Zwicky deduced an enormous mass for the Coma Cluster. When we sum up all of its galaxies' estimated masses, Coma ranks among the largest and most massive galaxy clusters in the universe. Even so, the cluster does not contain enough visible matter to account for the observed speeds of its member galaxies. Matter seems to be missing. If you apply Newton's law of gravity and assume that the cluster does not exist in an odd state of expansion or collapse, you can calculate what the characteristic average speed of its galaxies ought to be. All you need is the size of the cluster and an estimate of its total mass. The mass, acting over distances characterized by the cluster's size, determines how rapidly the galaxies must move to avoid falling into the cluster's center or escaping from the cluster entirely. In a similar calculation, as Newton showed, you can derive the speed at which each of the planets at its particular distance from the Sun must move in its orbit. Far from being magic, these speeds satisfy the gravitational circumstance in which each planet finds itself. If the Sun suddenly acquired more mass, Earth and everything else in the solar system would need larger velocities to stay in their current orbits. With too much speed, however, the Sun's gravity will be insufficient to maintain everybody's orbit. If Earth's orbital speed were more than the square root of 2 times its current speed, our planet would achieve escape velocity and, you guessed it, escape the solar system. We can apply the same reasoning to much larger objects, such as our own Milky Way galaxy, in which stars move in orbits that respond to the gravity from all the other stars, or in clusters of galaxies, where each of the galaxies likewise feels the gravity from all the other galaxies. As Einstein once wrote to honor Isaac Newton, "Look unto the stars to teach us how the master's thoughts can reach us. Each one follows Newton's math silently along its path." When we examine the Coma Cluster, as Zwicky did during the 1930s, we find that its member galaxies all move more rapidly than the escape velocity for the cluster, but only if we establish that velocity from the sum of all the galaxy masses taken one by one, which we estimate from the galaxy's brightnesses. The cluster should therefore swiftly fly apart, leaving barely a trace of its beehive existence after just a few 100 million years, perhaps a billion, had passed. But the cluster is more than 10 billion years old, nearly as old as the universe itself. And so was born what remains the longest-standing mystery in astronomy. Through the decades that followed Zwicky's work, other galaxy clusters revealed the same problem. So Coma could not be blamed for being odd. Then whom should we blame? Newton? No, his theories had been examined for 250 years and passed all tests. Einstein? No. The formidable gravity of galaxy clusters does not rise high enough to require the full hammer of Einstein's general theory of relativity, just 2 decades old when Zwicky did his research. Perhaps the missing mass needed to bind the Coma Cluster's galaxies does exist, but in some unknown, invisible form. For a time, astronomers renamed the missing mass problem the missing light problem, since the mass had been strongly inferred from the excess of gravity. Today, with better determinations of the masses of galaxy clusters, astronomers use the moniker dark matter, although dark gravity would be more precise. The dark matter problem reared its invisible head a second time. In 1976, Vera Rubin, an astrophysicist at the Carnegie Institution of Washington, discovered a similar missing mass anomaly within spiral galaxies themselves. Studying the speeds at which stars orbit their galaxy centers, Rubin first found what she expected. Within the visible disk of each galaxy, the stars farther from the center move at greater speeds than stars close in. The farther stars have more matter between themselves and the galaxy center, requiring higher speeds to sustain their orbits. Beyond the galaxy's luminous disk, however, we can still find some isolated gas clouds and a few bright stars. Using these objects as tracers of the gravity field outside the galaxy, where visible matter no longer adds to the total, Rubin discovered that their orbital speeds, which should have fallen with increasing distance out there in Nowheresville, in fact remained high. These largely empty volumes of space, the rural regions of each galaxy, contain too little visible matter to explain the orbital speeds of the tracers. Rubin correctly reasoned that some form of dark matter must lie in these far-out regions, well beyond the visible edge of each spiral galaxy. Indeed, the dark matter forms a kind of halo around the entire galaxy. This halo problem exists under our noses, right in our own Milky Way galaxy. From galaxy to galaxy and from cluster to cluster, the discrepancy between the mass in visible objects and the total mass of systems ranges from a factor of just 2 or 3 up to factors of many hundreds. Across the universe, the factor averages to about 6. That is, cosmic dark matter enjoys about 6 times the mass of all the visible matter. Over the past 25 years, further research has revealed that most of the dark matter cannot consist of non-luminous ordinary matter. This conclusion rests on 2 lines of reasoning. First, we can eliminate with near certainty all plausible familiar candidates, like the suspects in a police lineup, Could the dark matter reside in black holes? No, we think that we would have detected this many black holes from their gravitational effects on nearby stars. Could it be dark clouds? No, they would absorb or otherwise interact with light from stars behind them, which real dark matter doesn't do. Could it be interstellar planets, asteroids, and comets, all of which produce no light of their own? It's hard to believe that the universe would manufacture 6 times as much mass in planets as in stars. That would mean 6,000 Jupiters for every star in the galaxy, or worse yet, 2 million Earths. In our own solar system, for example, everything that is not the Sun adds to a paltry 0.2% of the Sun's mass. Thus, as best we can figure, the dark matter doesn't simply consist of matter that happens to be dark. Instead, it's something else altogether. Dark matter exerts gravity according to the same rules that ordinary matter follows, but it does little else that might allow us to detect it. Of course, we are hamstrung in this analysis by not knowing what the dark matter is. The difficulties of detecting dark matter, intimately connected with our difficulties in perceiving what it might be, raise the question: if all matter has mass, and all mass has gravity, does all gravity have matter? We don't know. The name dark matter presupposes the existence of a kind of matter that has gravity and that we don't yet understand. But maybe it's the gravity that we don't understand. To study dark matter beyond deducing its existence, astrophysicists now seek to learn where the stuff collects in space. If dark matter existed only at the outer edges of galaxy clusters, for example, then the galaxy's velocities would show no evidence of a dark matter problem, because the galaxy's speeds and trajectories respond only to sources of gravity interior to their orbits. If the dark matter occupied only the cluster's centers, then the run of galaxy speeds as measured from the center of the cluster out to its edge would respond to ordinary matter alone. But the speeds of galaxies in clusters reveal that the dark matter permeates the entire volume occupied by the orbiting galaxies. In fact, the locations of ordinary matter and dark matter loosely coincide with each other. Several years ago, a team led by the American astrophysicist J. Anthony Tyson, then at Bell Labs and now at UC Davis, produced the first detailed map of the distribution of dark matter's gravity in and around a titanic cluster of galaxies. Wherever we see big galaxies, we also find a higher concentration of dark matter within the cluster. The converse is also true: regions with no visible galaxies have a dearth of dark matter. The discrepancy between dark and ordinary matter varies significantly from one astrophysical environment to another, but it becomes most pronounced for large entities such as galaxies and galaxy clusters. For the smallest objects, such as moons and planets, no discrepancy exists. Earth's surface gravity, for example, can be explained entirely by what's under our feet. So if you are overweight on Earth, don't blame dark matter. Dark matter also has no bearing on the moon's orbit around Earth, nor on the movements of the planets around the sun. But we do need it to explain the motions of stars around the center of the galaxy. Does a different kind of gravitational physics operate on the galactic scale? Probably not. More likely, dark matter consists of matter whose nature we have yet to divine, and which clusters more diffusely than ordinary matter does. Otherwise, we would find that 1 in every 6 pieces of dark matter has a chunk of ordinary matter clinging to it. So far as we can tell, that's not the way things are. At the risk of inducing depression, astrophysicists sometimes argue that all the matter that we have come to know and love in the universe, the stuff of stars, planets, and life, are mere buoys afloat in a vast cosmic ocean of something that looks like nothing. But what if this conclusion were entirely wrong? When nothing else seems to work, some scientists will understandably, and quite rightly, question the fundamental laws of physics that underlies the assumptions made by others who seek to understand the universe. During the early 1980s, the Israeli physicist Mordechai Milgram of the Weizmann Institute of Science in Rehovot, Israel, suggested a change in Newton's laws of gravity, a theory now known as MOND. Accepting the fact that standard Newtonian dynamics operates successfully on size scales smaller than galaxies, Milgram suggested that Newton needed some help in describing gravity's effects at distances the sizes of galaxies and galaxy clusters. within which individual stars and star clusters are so far apart that they exert relatively little gravitational force on each other. Milgrom added an extra term to Newton's equation, specifically tailored to come to life at astronomically large distances. Although he invented MOND as a computational tool, Milgrom didn't rule out the possibility that his theory could refer to a new phenomenon of nature. MOND has had only limited success. The theory can account for the movement of isolated objects in the outer reaches of many spiral galaxies, but it raises more questions than it answers. MOND fails to predict reliably the dynamics of more complex configurations, such as the movement of galaxies in binary and multiple systems. Furthermore, the detailed map of the cosmic background radiation produced by the WMAP satellite in 2003 allowed cosmologists to isolate and measure the influence of dark matter in the early universe. Because these results appear to correspond to a consistent model of the cosmos based on conventional theories of gravity, MOND has lost many adherents. Cosmic history, matter in the universe had already begun to coalesce into the blobs that would become clusters and superclusters of galaxies. But the cosmos was expanding all along, and would double in size during its next 500,000 years. So the universe responds to two competing effects. Gravity wants to make stuff coagulate, but the expansion wants to dilute it. If you do the math, you rapidly deduce that the gravity from ordinary matter could not win this battle by itself. It needed the help of dark matter, without which we would be living, actually not living, in a universe with no structure, no clusters, no galaxies, no stars, no planets, no people. How much gravity from dark matter did it need? 6 times as much as that provided by ordinary matter itself. This analysis leaves no room for MOND's little corrective terms in Newton's laws. The analysis doesn't tell us what dark matter is, only that dark matter's effects are real, and that, try as you may, you cannot credit ordinary matter for it. Dark matter plays another crucial role in the universe. To appreciate all that the dark matter has done for us, go back in time to a couple of minutes after the Big Bang, when the universe was still so immensely hot and dense that hydrogen nuclei could fuse together. This crucible of the early cosmos forged hydrogen into helium, along with trace amounts of lithium, plus an even smaller amount of deuterium, which is a heavier version of the hydrogen nucleus, with a neutron added to the proton. This mixture of nuclei provides another cosmic fingerprint of the Big Bang, a relic that allows us to reconstruct what happened when the cosmos was a few minutes old. In creating this fingerprint, the prime mover was the strong nuclear force, the force that binds protons and neutrons within the nucleus, and not gravity, a force so weak that it gains significance only as particles assemble themselves by the trillions. By the time the temperature dropped below a threshold value, nuclear fusion throughout the universe had made 1 helium nucleus for every 10 hydrogen nuclei. The universe had also turned about 1 part in 1,000 of its ordinary matter into lithium nuclei, and 2 parts in 100,000 into deuterium. If dark matter did not consist of some non-interacting substance but was instead made of dark ordinary matter, matter with normal fusion privileges, then because the dark matter packed 6 times as many particles into the tiny volumes of the early universe as ordinary matter did, its presence would have dramatically increased the fusion rate of hydrogen. The result would have been a noticeable overproduction of helium, in comparison with the observed amount, and the birth of a universe notably different to the one that we inhabit. Helium is one tough nucleus, relatively easy to make but extremely difficult to fuse into other nuclei. Because stars have continued to make helium from hydrogen in their cores, while destroying relatively little helium through more advanced nuclear fusion. We may expect that the places where we find the lowest amounts of helium in the universe should have no less helium than what the universe produced during its first few minutes. Sure enough, galaxies whose stars have only minimally processed their ingredients show that 1 in 10 of their atoms consists of helium, just as you would expect from the Big Bang birthday suit of the cosmos. So long as the dark matter then present did not participate in the nuclear fusion that created nuclei. So, dark matter is our friend. But astrophysicists understandably grow uncomfortable whenever they must base their calculations on concepts they don't understand, even though this wouldn't be the first time they've done so. Astrophysicists measured the energy output of the Sun, for instance, long before anybody knew that thermonuclear fusion was responsible. Back in the 19th century, before the introduction of quantum mechanics and the discovery of other deep insights into the behavior of matter on its smallest scales, fusion didn't even exist as a concept. Unrelenting skeptics might compare the dark matter of today with the hypothetical, now defunct, ether, proposed centuries ago as the weightless, transparent medium through which light moved. For many years, until a famous 1887 experiment in Cleveland performed by Albert Michelson and Edward Morley, physicists assumed that the ether must exist, even though not a shred of evidence supported this presumption. Known to be a wave, light was thought to require a medium through which to move, much as sound waves move through air. Light turns out to be quite happy, however, traveling through the vacuum of space, devoid of any supporting medium. Unlike sound waves, however, which do consist of vibrations of the air, light waves propagate themselves. But dark matter ignorance differs fundamentally from ether ignorance. While ether amounted to a placeholder for our incomplete understanding, the existence of dark matter derives not from mere presumption but from the observed effects of its gravity on visible matter. We're not inventing dark matter out of thin space. Instead, we deduce its existence from observational facts. Dark matter is just as real as the 100-plus planets discovered in orbit around stars other than the Sun, almost all of them found solely by their gravitational influence on their host stars. The worst that can happen is that physicists might discover that the dark matter does not consist of matter at all, but of something else, yet they cannot argue it away. Could dark matter be the manifestation of forces from another dimension? Or of a parallel universe intersecting ours? Even so, none of this would change the successful invocation of dark matter's gravity in the equations that we use to understand the formation and evolution of the universe. Other unrelenting skeptics might declare that seeing is believing. A seeing is believing approach to life works well in many endeavors, including mechanical engineering, fishing, and perhaps dating. It's also good, apparently, for residents of Missouri. But it doesn't make for good science. Science is not just about seeing. Science is about measuring, preferably with something that's not your own eyes, which are inextricably conjoined with the baggage of your brain, preconceived ideas, postconceived notions, imagination unchecked by reference to other data, and bias. Having resisted attempts to detect it directly on Earth for 3/4 of a century, dark matter has become a type of Rorschach test of the investigator. Some particle physicists say the dark matter must consist of some ghostly class of undiscovered particles that interact with matter via gravity, but otherwise interact with matter or light only weakly, or not at all. This sounds off the wall, but the suggestion has precedent. Neutrinos, for instance, are well known to exist, though they interact extremely weakly with ordinary light and matter. Neutrinos from the Sun, 2 neutrinos for every helium nucleus made in the solar core, travel through the vacuum of space at nearly the speed of light, but then pass through Earth as though it did not exist. The tally, night and day, 100 billion neutrinos from the Sun enter, then exit each square inch of your body every second. But neutrinos can be stopped. Every rare once in a while they interact with matter via nature's weak nuclear force. And if you can stop a particle, you can detect it. Compare neutrinos' elusive behavior with that of the invisible man, as good a candidate for the dark matter as anything else. He could walk through walls and doors as though they were not there. Although equipped with these talents, why didn't he just drop through the floor into the basement? If we can build sufficiently sensitive detectors, the particle physicists' dark matter particles may reveal themselves through familiar interactions. Or they may reveal their presence through forces other than the strong nuclear force, the weak nuclear force, and electromagnetism. These 3 forces mediate all interactions between and among all known particles. So the choices are clear. Either dark matter particles must wait for us to discover and to control a new force or class of forces through which the particles interact, or else dark matter particles interact via normal forces, but with staggering weakness. Mond theorists see no exotic particles in their Rorschach tests. They think gravity, not particles, is what needs fixing. And so they brought forth modified Newtonian dynamics, a bold attempt that seems to have failed, but doubtless the precursor of other efforts to change our view of gravity rather than our census of subatomic particles. Other physicists pursue what they call TOEs, or theories of everything. In a spin-off of one version, our own universe indeed lies near a parallel universe, with which we interact only through gravity. You'll never run into any matter from that parallel universe, but you might feel its tug, crossing into the spatial dimensions of our own universe. Imagine a phantom universe right next to ours, revealed to us only through its gravity. Sounds exotic and unbelievable, but probably not any more so than the first suggestions that Earth orbits the Sun, or that our galaxy is not alone in the universe. So, dark matter's effects are real. We just don't know what the dark matter is. It seems not to interact through the strong force, so it cannot make nuclei. It hasn't been found to interact through the weak nuclear force, something even elusive neutrinos do. It doesn't seem to interact with the electromagnetic force, so it doesn't make molecules, or absorb or emit or reflect or scatter light. It does exert gravity, however, to which ordinary matter responds. That's it. After all these years of investigation, astrophysicists haven't discovered it doing anything else. Detailed maps of the cosmic background radiation have demonstrated that dark matter must have existed during the first 380,000 years of the universe. We also need dark matter today in our own galaxy and in galaxy clusters to explain the motions of objects they contain. But as far as we know, the march of astrophysics has not yet been derailed or stymied by our ignorance. We simply carry dark matter along as a strange friend, and invoke it where and when the universe requires it of us. In what we hope is the not-so-distant future, the fun will continue as we learn to exploit dark matter. Once we figure out what the stuff is made of. Imagine invisible toys, cars that pass through one another, or super stealth airplanes. The history of obscure and obtuse discoveries in science is rich with examples of clever people who came later and who figured out how to exploit such knowledge for their own gain or for the benefit of life on Earth. Let there be more dark. The cosmos, we now know, has both a light and a dark side. The light side embraces all familiar heavenly objects, the stars, which group by the billions into galaxies, as well as the planets and smaller cosmic debris that may not produce visible light but do emit other forms of electromagnetic radiation, such as infrared or radio waves. We have discovered that the dark side of the universe embraces the puzzling dark matter, detected only by its gravitational influence on visible matter but otherwise of completely unknown form and composition. A modest amount of this dark matter may be ordinary matter that remains invisible because it produces no detectable radiation. But, as detailed in the previous chapter, the great bulk of the dark matter must consist of non-ordinary matter, whose nature continues to elude us, except for its gravitational force on matter we can see. Beyond all issues concerning dark matter, the dark side of the universe has another, entirely different aspect. One that resides not in matter of any kind, but in space itself. We owe this concept, along with the amazing results that it implies, to the father of modern cosmology, none other than Albert Einstein himself. 90 years ago, while the newly perfected machine guns of World War I slaughtered soldiers by the thousands a few hundred miles to the west, Albert Einstein sat in his office in Berlin, pondering the universe. As the war began, Einstein and a colleague had circulated an anti-war petition among his peers, gathering 2 other signatures in addition to their own. This act set him apart from his fellow scientists, most of whom had signed an appeal to aid Germany's war effort, and ruined his colleague's career. But Einstein's engaging personality and scientific fame allowed him to keep the esteem of his peers. He continued his efforts to find equations that could accurately describe the cosmos. Before the war ended, Einstein achieved success, arguably his greatest of all. In November 1915, he produced his general theory of relativity, which describes how space and matter interact. Matter tells space how to bend, and space tells matter how to move. To replace Isaac Newton's mysterious action at a distance, Einstein viewed gravity as a local warp in the fabric of space. The sun, for example, creates a sort of dimple, bending space most noticeably at distances closest to it. The planets tend to roll into this dimple, but their inertia keeps them from falling all the way in. Instead, they move in orbits around the Sun that keep them at a nearly constant distance from the dimple in space. Within a few weeks after Einstein published his theory, the physicist Karl Schwarzschild, diverting himself from the horrors of life in the German army, used Einstein's concept to demonstrate that an object with sufficiently strong gravity will create a singularity in space. At such a singularity, space bends completely around the object and prevents anything, including light, from leaving its immediate vicinity. We now call these objects. Einstein's theory of general relativity led him to the key equation he had been seeking, one that links the contents of space to its overall behavior. Studying this equation in the privacy of his office, creating models of the cosmos in his mind, Einstein almost discovered the expanding universe, a dozen years before Edwin Hubble's observations revealed it. Einstein's basic equation predicts that in a universe in which matter has a roughly even distribution, space cannot be static. The cosmos cannot just sit there, as our intuition insists that it should, and as all astronomical observations until that time implied. Instead, the totality of space must always be either expanding or contracting. Space must behave something like the surface of an inflating or deflating balloon, but never like the surface of a balloon with constant size. This worried Einstein. For once, this bold theorist, who mistrusted authority and had never hesitated to oppose conventional physics ideas, felt that he had gone too far. No astronomical observations suggested an expanding universe, because astronomers had only documented the motions of nearby stars and had not yet determined the faraway distances to what we now call galaxies. Rather than announcing to the world that the universe must either be expanding or contracting, Einstein returned to his equation, seeking a way to immobilize the cosmos. He soon found one. Einstein's basic equation allowed for a term with a constant but unknown value that represents the amount of energy contained in every cubic centimeter of empty space. Because nothing suggested that this constant term should have one value or another, in his first pass Einstein had set it equal to 0. Now Einstein published a scientific article to demonstrate that if this constant term, which cosmologists later named the Cosmological Constant, had a particular value, then space could be static. Then theory would no longer conflict with observations of the universe, and Einstein could regard his equation as valid. Einstein's solution encountered grave difficulties. In 1922, a Russian mathematician named Alexander Friedmann proved that Einstein's static universe must be unstable, like a pencil balanced on its point. The slightest ripple or disturbance would cause space either to expand or to contract. Einstein first proclaimed Friedmann mistaken, but then, in a generous act typical of the man, published an article retracting that claim and pronouncing Friedmann correct after all. As the 1920s ended, Einstein was delighted to learn of Hubble's discovery that the universe is expanding. According to George Gaimov's recollections, Einstein pronounced the cosmological constant his greatest blunder. Except for a few cosmologists who continued to invoke a non-zero cosmological constant to explain certain puzzling observations, most of which later proved to be incorrect. Scientists the world over sighed with relief that space had proven to have no need of this constant. Or so they thought. The great cosmological story at the end of the 20th century, the surprise that stood the world of cosmology on one ear and sang a different tune into the other, resides in the stunning discovery, first announced in 1998, that the universe does have a non-zero cosmological constant. Empty space does indeed contain energy, named dark energy, and possesses highly unusual characteristics that determine the future of the entire universe. Themes in cosmologists' thinking during the 70 years following Hubble's discovery of the expanding universe. Einstein's fundamental equation allows for the possibility that space can have curvature, described mathematically as positive, zero, or negative. Zero curvature describes flat space, the kind that our minds insist on as the only possibility, which extends to infinity in all directions, like the surface of an infinite chalkboard. In contrast, a positively curved space corresponds in analogy to the surface of a sphere, a two-dimensional space whose curvature we can see by using the third dimension. Notice that the center of the sphere, the point that appears to remain stationary as its two-dimensional surface expands or contracts, resides in this third dimension and appears nowhere on the surface that represents all of space. Just as all positively curved surfaces include only a finite amount of area, all positively curved spaces contain only a finite amount of volume. A positively curved cosmos has the property that if you journey outward from Earth for a sufficiently long time, you will eventually return to your point of origin, like Magellan circumnavigating our globe. Unlike positively curved spherical surfaces, negatively curved spaces extend to infinity, even though they are not flat. A negatively curved two-dimensional surface resembles the surface of an infinitely large saddle. It curves upward in one direction and downward in another. If the cosmological constant equals 0, we can describe the overall properties of the universe with just two numbers. One of these, called the Hubble constant, measures the rate at which the universe is expanding now. The other measures the curvature of space. During the second half of the 20th century, almost all cosmologists believed that the cosmological constant was 0, and saw measuring the cosmic expansion rate and the curvature of space as their primary research agenda. Both of these numbers can be found from accurate measurements of the speeds at which objects located at different distances are receding from us. The overall trend between distance and velocity. The rate at which the recession velocities of galaxies increase with increasing distance yields the Hubble constant, whereas small deviations from this general trend, which appear only when we observe objects at the greatest distances from us, will reveal the curvature of space. Whenever astronomers observe objects many billion light-years from the Milky Way, they look so far back in time that they see the cosmos not as it is now but as it was when significantly less time had elapsed since the Big Bang. Observations of galaxies located 5 billion or more light-years from the Milky Way allow cosmologists to reconstruct a significant part of the history of the expanding universe. In particular, they can see how the rate of expansion has changed with time, the key to determining the curvature of space. This approach works, at least in principle, because the amount of space's curvature induces subtle differences in the rate at which the universal expansion had changed through past billions of years. In practice, astrophysicists remained unable to fulfill this program, because they could not make sufficiently reliable estimates of the distances to galaxy clusters many billion light-years from Earth. They had another arrow in their quiver, however. If they could measure the average density of all the matter in the universe, that is, the average number of grams of material per cubic centimeter of space, they could compare this number with the critical density, a value predicted by Einstein's equations that describe the expanding universe. The critical density specifies the exact density required for a universe with zero curvature of space. If the actual density lies above this value, the universe has positive curvature. In that case, assuming that the cosmological constant equals 0, the cosmos will eventually cease expanding and start contracting. If, however, the actual density exactly equals the critical density, or falls below it, then the universe will expand forever. Exact equality of the actual and critical values of the density occurs in a cosmos with zero curvature, whereas in a negatively curved universe, the actual density is less than the critical density. By the mid-1990s, cosmologists knew that even after including all the dark matter they had detected, the total density of matter in the universe only came to about 1/4 of the critical density. This result hardly seems astounding, although it does imply that the cosmos will never cease expanding, and that the space in which all of us live must be negatively curved. It hurt theoretically oriented cosmologists, however, because they had come to believe that space must have zero curvature. This belief rested on the inflationary model of the universe, named at a time of a steeply rising consumer price index. In 1979, Alan Guth, a physicist working at the Stanford Linear Accelerator Center in California, hypothesized that during its earliest moments, the cosmos expanded at an incredibly rapid rate, so rapidly that different bits of matter accelerated away from one another, reaching speeds far greater than the speed of light. But doesn't Einstein's theory of special relativity make the speed of light a universal speed limit for all motion? Not exactly. Einstein's limit applies only to objects moving within space and not the expansion of space itself. During the inflationary epoch, which lasted only from about 10 to 37 second to 10 to 34 second after the Big Bang, the cosmos expanded by a factor of about 1050. What produced this enormous cosmic expansion? Guth speculated that all of space must have undergone a phase transition, something analogous to what happens when liquid water quickly freezes into ice. After some crucial tweaking by his colleagues in the Soviet Union, the United Kingdom, and the United States, Guth's idea became so attractive that it has dominated theoretical models of the extremely early universe for 2 decades. And what makes inflation such an attractive theory? The inflationary era explains why the universe, in its overall properties, looks the same in all directions, everything that we can see inflated from a single tiny region of space, converting its local properties into universal ones. Other advantages, which need not detain us here, accrue to the theory, at least among those who create model universes in their minds. One additional feature deserves emphasis, however. The inflationary model makes a straightforward, testable prediction: space in the universe should be flat, neither positively nor negatively curved, but just as flat as our intuition imagines it. According to this theory, the flatness of space arises from the enormous expansion that occurred during the inflationary epoch. Picture yourself, in analogy, on the surface of a balloon, and let the balloon expand by a factor so large that you lose track of the zeros. After this expansion, the part of the balloon's surface that you can see will be flat as a pancake. So too should be all the space that we can ever hope to measure, if the inflationary model actually describes the real universe. Space flat. During the 1980s and 1990s, many theoretically minded cosmologists believed that because the inflationary model must be valid, new data would eventually close the cosmic mass gap, the difference between the total density of matter, which pointed toward a negatively curved universe, and the critical density, seemingly required to achieve a cosmos with flat space. Their beliefs carried them buoyantly onward, even as observationally oriented cosmologists mocked their over-reliance on theoretical analysis. And then the mocking stopped. In 1998, 2 rival teams of astronomers announced new observations implying the existence of a non-zero cosmological constant, not the very number that Einstein had proposed in order to keep the universe static, but another, quite different value. One that implies that the universe will expand forever at an ever-increasing rate. If theorists had proposed this for yet another model universe, the world would have little noted nor long remembered their effort. Here, however, reputable experts in observing the real universe had mistrusted one another, checked on their rivals' suspicious activities, and discovered that they agreed on the data and their interpretation. The observational results not only implied a cosmological constant different from zero, but also assigned to that constant a value that makes space flat. What's that you say? The cosmological constant flattens space? Aren't you suggesting, like the Red Queen in Alice in Wonderland, that we each believe 6 impossible things before breakfast? More mature reflection may, however, convince you that if apparently empty space does contain energy, that energy must contribute mass to the cosmos, just as Einstein's famous equation, E equals mc squared, implies. If you've got some E, you can conceive it as a corresponding amount of m equal to E divided by c2. Then the total density must equal the total of the density contributed by matter, plus the density contributed by energy. The new total density is what we must compare with the critical density. If the two are equal, space must be flat. This would satisfy the inflationary model's prediction of flat space, for it does not care whether the total density in space arises from the density of matter, or the matter equivalent provided by the energy in empty space, or a combination of the two. The crucial evidence suggesting a non-zero cosmological constant, and thus the existence of dark energy, came from astronomers' observations of a particular type of exploding star or supernova, stars that die spectacular deaths in titanic explosions. These supernovae, called either type Ia or SNIAs, differ from other types, which occur when the cores of massive stars collapse after exhausting all possibilities of producing more energy by nuclear fusion. In contrast, SNIAs owe their origin to white dwarf stars that belong to binary star systems. Two stars that happen to be born close to one another will spend their lives performing simultaneous orbits around their common center of mass. If one of the two stars has more mass than the other, it will pass more rapidly through its prime of life, and in most cases will then lose its outer layers of gas, revealing its core to the cosmos as a shrunken, degenerate, white dwarf. An object no larger than Earth but containing as much mass as the Sun, physicists call the matter in white dwarfs degenerate, because it has such a high density, more than 100,000 times the density of iron or gold, that the effects of quantum mechanics act on matter in bulk form, preventing it from collapsing under its enormous self-gravitational forces. A white dwarf in mutual orbit with an aging companion star attracts gaseous material